How are you today? In Chapter 7, we have two topics. One is work and power, and another is kinetic energy and work energy principle. First of all, let's make a review of what we have learned in previous classes. Kinematics is a study that describes motion of objects. On the other hand, dynamics, in terms of Newton's law, answers the question of how object moves. The motion of an object can be complicated. Translational motion might be a little bit easy place for us to start with. Particle is a model we use to represent an object which we don't care about its rotation. So, particle is a point with no spatial extension. We attribute all the mass of the object on that point. Then, we need a reference frame. In inertial reference frame, Newton's laws hold. And then, we set a coordinate so that we are able to use mathematical tools like calculus to make analysis of the motion. Rectangular coordinate and polar coordinates are two of them we frequently use. Now, we have position vector. We know displacement delta r. We define velocity as the change rate of displacement with time. It is the derivative of delta r with respect to time t. Acceleration is the second derivative of displacement r with respect to time t. It measures the change rate of velocity. If the position vector as a function of time t is given, we understand the position of the object at any moment. If we cancel out the time t, we will have the relation between the three coordinates x, y, z. This equation is called the trajectory equation. Following are some of the typical motions. For linear motion at constant velocity, the acceleration equals to 0. For linear motion at constant acceleration, the tangential acceleration equals to constant, but the normal acceleration equals to 0. For curvilinear motion, the acceleration vector is not equal to 0. The tangential component of the acceleration equals to the change rate of the magnitude of the velocity. The normal component equals to v squared over r, where r, the capital R, is the curvature radius of the motion. For uniform circular motion, the tangential component at equal to 0, but the an equal to v squared over r. For circular motion at constant acceleration, the at equals constant, an equal to v squared over r. So the magnitude of the acceleration a equals to square root of at squared plus an squared. There are two kinds of problems in kinematics. The first one is that the position of the object is given. You are asked to find the velocity and acceleration. All you have to do is the derivative. The second problem is that the acceleration is given. You are supposed to find the velocity and position. You just need to do the integral. It is quite easy as well. The relation between acceleration and force is governed by Newton's second law. Originally, Newton wrote his second law as F equals to dp dt, the change rate of momentum. For most cases, the motion speed of objects is much smaller than the speed of light. The mass of an object does not change during the motion. So, F equals to m dv dt equals to mass m multiplied by the second derivative of r with respect to time t. So, you solve above differential equation, you find the position vector r as a function of time t. Now we have position, velocity, acceleration. We understand velocity is the derivative of position vector with respect to time t. It is the measure of the change rate of position with time. The larger the velocity, the faster the object moves. We understand acceleration is the derivative of velocity with time. It is the change rate of velocity with time. The larger the acceleration, the larger the force acting on the object. You may wonder why we don't define a quantity as the derivative of acceleration with time. That would be the change rate of force with time. However, we find that this quantity is not so meaningful. On the other hand, why don't we make some combinations of the quantities we have already studied a lot of time? It might be fruitful. These combinations are usually multiplications other than additions. Let's take a look at the following quantities: position r, velocity v, acceleration a, force F, displacement delta r, change of velocity, time duration delta t. What about the force multiplied with displacement? Force F multiplied with displacement r equals to work done by the force during the motion. In later chapters, you will find some of these useful combinations.